In this tutorial, we're talking about momentum and impulse and how they are related to each other. Momentum is another way of explaining motion, so it's a part of that dynamics in terms of mechanics of physics. And it is similar to inertia, but there's a slight difference. Inertia is the tendency of an object to maintain its original state of motion. So it's the first law of motion. An object at rest stays at rest, and an object in motion stays in motion. It is only dependent upon by its mass. The more mass something has, the more difficult it is to change its motion. So if two objects are at rest, let's say a car and a bicycle, it's more difficult to move the car because it has more mass and hence more inertia. Momentum is really only the moving component of that inertia statement. So an object in motion wants to stay in motion is kind of momentum. So it's inertia in motion. It is only the motion part of that. So it depends on velocity and mass. And think of it as how difficult it is to stop a moving object. So if we have that car and that bicycle, which one is more difficult to stop if they're moving at the same velocity? Well, the car is, because it has more mass. However, it also depends on that velocity as well. So even if we have something that is moving very slow, if it has a lot of mass, it's still difficult to stop. So if we think of maybe an ocean liner, a big boat, a boat, even though it might just be drifting very slowly, is very difficult to stop because it has a lot of mass. It is a vector, which means it has a direction. And so it is not just speed, it's dependent upon the velocity. Think of it this way when dealing with momentum. Let's say you want to break a door down. In order to break a door down, we need to have a lot of mass. That's why we use a battering ram, so we can get as large a mass as possible. And we also need it to be moving as fast as possible. But it depends on the direction as well. So of course it wouldn't make sense to swing the battering ram away from the door. That's not going to break the door down. We need that direction towards the door. The symbol might not make sense. It is the letter P. And whereas nobody has ever written down in history why we use the symbol P for momentum, some people speculate that when we were first talking about momentum, we were talking about the forward progress of an object. And hence we use the letter P. Again, that's complete speculation, but hopefully that might help you remember that the symbol is letter P. We definitely would not want to use letter M, because the equation is momentum is mass times velocity, and we wouldn't want to use the letter M for two things. Looking at the units, mass is measured in kilograms, and velocity is measured in meters per second. And so therefore our symbol, or our unit for momentum, is a kilogram times a meter per second. There is no special name for that. There's no abbreviation for that like there is for a Newton and a joule and a watt. It's simply a kilogram times a meter per second. Impulse, on the other hand, causes a change in momentum. Just like a force causes a change in velocity, causes an acceleration. The symbol for impulse could either be one of two things. You could either write it as a letter J, and I've never seen a reason why it's a letter J, but it could be a letter J, or it could be delta P. I've seen it both ways, either J or delta P for impulse. We will use delta P because it helps us understand it is the change in momentum. So it helps us remember what impulse actually is. The units would be the same as momentum. Just like if I find the change in mass of something or the change in velocity, let's say the velocity goes from 5 to 7 meters per second. It is changed by 2 meters per second. The change in something has the same units as the concept or the quantity itself. So the change in momentum has the same units as momentum itself. Kilograms times meters per second. Now, one other way that they are related is through the impulse momentum theorem. So the change in momentum is equal to the total force acting on that object times the time of impact. How much time is that force being applied? What this is saying is that if we want to decrease the force of impact, if we want this to be lower, for the same amount of change in momentum, we must make the time of impact larger. So what are some applications of this? Well, one application would be airbags in your car. An airbag is meant to bring you to a stop in a longer amount of time. So more time and therefore less force. Same as your seatbelt. It's meant to bring you to a stop in a longer amount of time. So longer time, less force to change your momentum. Another application might be somebody jumping out of an airplane with a parachute. As you land with your parachute, you bend your knees, and you might even roll afterwards. And by bending your knees and rolling, you're increasing your time of impact and therefore decreasing the force on your body, making it safer for yourself. And in this way, people who jump out of 4-story buildings can sometimes survive the fall by increasing their time of impact. A lot of times what they'll do is faint, and so if their body is not rigid as they land, they kind of crumple and therefore increase the time of impact. And so your car as well, besides the airbag and the seat belts, your car has a crumple zone. And so as you crash the front end of your car, or maybe the back end, it's very easy to dent it, to crumple that car. And it's not a conspiracy. The whole idea is to increase the time of impact. It's a safety feature and therefore decrease the force.